Okay, now we're going to pick up what is in Chapter 2 of our textbook, and this is the idea of abstract data types, ADTs as they're known, and the data structures that are related to them. So let's go back for a second. We are focusing on doing these using an object-oriented design methodology. The idea there is, as with some of the other system methodologies, it is what is called divide and conquer. That is to break a larger problem into smaller problems, and each of those problems into smaller problems until you find something that you can solve and then implement, and then roll them back up into the larger problems until you finally have solved the entire thing. So the object-oriented approach, instead of looking at the tasks and the procedural aspects of what you're trying to design, looks at the things that are being manipulated. And this was going to drive out the data that is going to be necessary to be acted upon. So this is what you call data-driven versus a more procedural approach. The design that comes out of doing this kind of analysis is something that consists of what you call objects. Objects are representing these things. That's the formal term for a thing as a piece of data. And then these objects, which are specific things in the world, like a particular car, a particular cat, etc., are then represented by more abstract concepts, which we call classes. The objects themselves, the important thing here is that they combine both the data elements themselves plus all the legal operations on the data into what you would think of as a self-contained entity. And these entities, using what's called encapsulation, as we'll see, protect themselves from access from the outside world. And so the idea here is that from the outside, the objects in the form of the class abstractions will only allow certain operations, certain behaviors to be done to them, and internally the object can do satisfy these behaviors, the things that are requested of them, in many different ways, and the outside user, the client, the application user, doesn't need to know, or actually should never know, exactly how it's being done inside. That's the important concept to take away from this. So here is a quote from Grady Booch, one of the most famous object-oriented design people. He said, here, read the specification of the software you want to build. Those are based upon the requirements you've gotten. Underline the verbs if you're after procedural code. Those are the tasks. And the nouns if you aim for an object-oriented program, because those are ultimately the objects and then the classes based upon those. So if you remember back to our previous lectures, the example of baking a cake, which was shown as a hierarchical task-oriented chart. Here, if you take that and you sort of turn it upside down, and instead of looking at the processes that you need to do, like bake and mix and etc., here what you look for is the objects that appear in this application domain. So for example, we have an oven, we have a bowl, we have eggs, etc., etc. Each of those things has got attributes. And so, for example, the oven has, it's an energy source, it has a particular size, it has a particular temperature at a particular time, it has a number of racks, etc. The bowl has capacity, how much is it filled, the eggs size or number, however you want to measure it. But I think you get the idea that those are in fact the data that the class is going to be managing for you. And then the responsibilities are the operations. These are actually what the object is going to offer to the outside world, and then it will manage itself internally to make these things happen. So for example, the oven as an object allows you to turn it on. It allows you to turn it off, set a desired temperature. Those are the functions that the class is going to offer to the outside world, and likewise with the other ones too. So you see this is a sort of an inside-out view of system design. That is the essence of doing object-oriented design. Now here's one that is more complex. We won't necessarily go into it in great detail, but if you look at it, this is a car. And the relationships between these things, we'll talk more about that later, are a little bit more explicit. This is in fact a class diagram, a UML class diagram with some notations on it to give you a little more detail as to what's going on. So you have this concept of a car is a vehicle. That's from the bottom to the top. You see the arrow pointing upwards. A lorry, this is actually a European British example. That would be a truck for us. A truck is also a vehicle. So a vehicle, though both of those things are specialized versions of a more general concept of vehicle. So a vehicle has a wheelbase, how far apart are the wheels, what's the maximum horsepower, how many seats does it have. Those are all essentially variables, and then the functions or methods that a vehicle offers to the outside world would be press the accelerator, turn the wheel, press the brake, etc. And then you'll see that's what we're most interested right now, but in a larger system you see that there are other classes and other types of objects out there, like person, or wheel is as it would be another type of object. And there are many different kinds of relationships. As you can see, there's association relationships, containment relationships. We'll talk a little bit more about that later. But it's the idea here of, a vehicle is made up of various components, and it has certain things that are part of it, whereas a person here is an owner and has a particular relationship in that way, and along with the idea of cardinality, that is how many of these things are there, etc. These are all things that you can find baked into one of these class diagrams. But for now, what we're focusing on is this idea of what an object can represent and what it can offer you. So we have different views of data. These data entities, the objects we're talking about, are really the nouns. The abstract objects that are being manipulated we represent as classes. The attributes inside of them that are being processed internally are called members. Those are variables. And the functions that operate on them internally and are offered to the outside world, some of them are, some of them aren't, some of them are public, some of them are private. Those are what we call methods. It's really synonym for function. So the data abstractions, there are different kinds of abstractions that we can talk about, but basically from our point of view, they separate a user's logical view of the data from the implementation view of the data. Okay, so we can look at data from multiple levels. The logical view answers questions like, what are the possible values? What are the valid operations on this data? And it says really nothing about how it's actually stored or manipulated internally or physically when it actually is run on a machine. The implementation view, however, is more specific. It's how is this data used, how is it physically stored, how is it implemented in a particular programming language that supports this. So as you can see, they're very different levels of abstraction. Data encapsulation, I mentioned this word before, sometimes called data hiding, is the formal term for separating the representation of the data, the physical representation, from the client applications that access it at a logical level, so they do not have to know anything about the physical representation. The concept of encapsulation puts the data itself in charge of itself. That is, what is accessible to the outside world and how those data members are actually processed. The details of how the processing done is hidden behind what you call an interface. By the way, this is not literally the same thing as a C++ interface, though you can use that to help implement these things. But in the more generic sense of the word interface, is that is what the outside, the user or client of these objects or classes would actually see in terms of what can be done to the data, what exists inside the data, etc. And it's the only thing that a client is allowed to interact with. Now, in fact, even if you didn't do much class programming in C++ or Java or some other class type language like that, object-oriented language, in fact, you've been using this even in C. So, for example, if you think of this as a black box, the object here, in a sense, and this is not literally an object inside of C++, though there is an integer object, which is a big integer. There is a separate object type or class type called integer in C++. But what we're talking about here is the int primitive, the same one that you knew from C. And you can think of it the same way. So in a sense, the int type, which is a primitive in C, C++, and most other languages, actually is acting like one of these object classes, in the sense that it defines what the type of the values are that it's representing. In fact, that there's a concept of what is the minimum, what is the maximum, so there's a range concept built in there. And then there are the operations. In the case of ints, they're all the ones that you typically know. The plus, minus, multiplication, division, modulo arithmetic, other kinds of relational operators, etc. Now, in fact, even though you use those in your programs, you do not know literally how they're being implemented, and honestly, you don't care. That is the essence of what we're looking for here. So that all of that stuff that's inside, all you see from the outside is the fact that one of these int things can represent an integer, a whole number in arithmetic and mathematics, and exactly of a particular size, int min to int max in this case, and you can do these things with it. Okay, how it's actually done, how it's actually stored, how big are these things in memory, where do they go in memory, how do you actually do these operations internally is again is a black box, and we want to keep it that way. So what we're talking about is actually having you design these black boxes and then implement them. The design of the black box is essentially what we call an ADT, an abstract data type. It's a model for describing data, a generalized kind of data that is manipulated in particular kinds of ways. That is what we call the behavior of the ADT, and it's the important point of view is that it is from the view of a user of the data, not an implementer. What do they define? They define the possible data values, the possible operations this data can have done to it. That's what we call the interface. And the behavior of these operations, exactly how do they work, that is what we call the semantics. Which means the meaning of these operations. So the ADT's operations and the values that it operates on, this is the important concept, at this level are completely independent of any specific implementation. That is the abstraction. Just before we get into some more of what goes on behind here, just so you know what we're referring to, there are many ADTs that we use all the time. Concepts like static arrays, that is, are fixed in memory at a particular time. Dynamic arrays, which are allowed to grow and shrink sometimes. Other things like linked lists, which can be sorted and unsorted, as we'll see in our text. Those are the next couple of chapters. Talk about those. Queues, which are lines, like a queue at a movie theater, etc. There's some concept of how you get into the line, how do you get it into the queue, how do you get out of the queue. Trees are an extremely important ADT. because of the nature of how they are searched, in particular how they're formed. They can take more storage, but they can be much, much faster to search. Heaps, you may or may not have heard of this. This is a particular kind of tree-based structure. It, because of the nature of how they are created and updated, they maintain an implicit ordering, which is very nice because then they can be used to implement things like priority queues, which are versions of queues where it's simply not the first in, first out, but is based upon a particular ordering. Other things, for example, like hash tables, hash maps, or just maps, are used to implement what are called associative arrays. That is, structures that instead of being looked up by array indexes are mapped from keys, that is values that are lookup values, to the actual values that are stored in the table or in the map. They do that using what's called a hash function, and then there's a lot that goes into maintaining such things, but in terms of lookups, they are extremely fast. And then graphs, probably the last thing we'll get to this semester, is a more general form of tree in the sense that they can actually represent not only tree structures where you cannot have any loops inside the structure. Here you can have multiple paths between elements in the graph, which is essentially a network, and so it's a more general form of tree in a sense. So this class is called data structures. So what the heck is a data structure then? Well, you can look at it in different ways. Here's one way. You can think of them as there's some kind of structure, obviously that's in the name, of data collections. Okay, these data collections are created so that they can hold and manage information of various types. Another way of thinking about it is it's a data organization and access strategy. So in other words, there are algorithms that are involved with manipulating these things such that you can then compare them. The two basic things we're going to be using for comparison of data structures against each other are how efficient are they in time, in other words, how fast are they, and how efficient are they in space, in other words, how much space do they take up. Some algorithms are very, very fast, but they need a lot of extra memory in order to operate well. Some are the opposite. They're slower, however, they take very little extra space. And so that you're going to see that, in fact, a lot of data structures involves trade-offs. Another way, we go back to the concept of design patterns. You can think of them as software design patterns for solving common problems that are data-oriented. However, the formal definition, the one that we'll use if you're ever asked what is a data structure, here is one. It's a concrete, that is, it's real, it's actually been implemented, physical implementation of a data abstraction, like our ADTs, and its associated operations, those are the behaviors, coded using selected algorithms, so an algorithm being a series of steps as a means to an end to achieve some particular result in some target programming language. So this is the big distinction, that it is a physical implementation. It is what you would call concrete versus the ADT, which is a more high-level abstraction that is seen more from the outside, whereas this is actually the internals of the how the data is stored and organized and manipulated. So it's really a collection of data elements plus the operations that implement the specifications of an ADT. Again, they're concrete versus abstract. A data structure can be decomposed into its individual elements because they are collections. And you want to typically be able to get at every one of the individual elements. The implementation implies there's some kind of physical arrangement, and that how that's actually done internally and on a real system is very important. However, again, that is all shielded. Here's the term again, encapsulated. So the details of how those things are done is actually hidden within the data structure itself. And not that you don't know or you can't examine how it's being done, but in terms of the basic the application programmer or the client, there is no need to know exactly how it's done, and in fact, usually you don't even want to know how it's being done. Some characteristics of data structures: they typically provide ways to insert data into this collection, some mechanism to traverse the memory. That's the formal term for give me the next one, give me the next one, give me the previous one, etc., in some kind of sequential fashion, one after the other. Some tools to find and then retrieve items from there, and then also to be able to remove items from the collection. So virtually every data structure we see does that. Usually, and in all the examples we're going to be working with, the data is of one type in a data structure. That is what is called homogeneous. The other kind would be called heterogeneous. And those are either primitives like ints or floats or doubles, or some more complex objects like classes that you would create. Not every language forces that to be true. There are some languages, let's say like Python or JavaScript, where some data structures like arrays can actually be heterogeneous and contain multiple different kinds of data types. But that's not what we're going to be focusing on. The majority of languages support the homogeneous style. Another concept is the data, the actual data, the elements that you're interested in, and the collections, the way that they're put together, are really logically separate entities. There is nothing that ties the data just to one type of collection. And so what that means is that any given data structure, from a theoretical point of view, can store any kind of data, but in practice, some are more effective or efficient than others, based upon the particular constraints that you're working with. So here's an analogy for our abstraction scheme. Here is a library. The data elements are the books in the library. The ADT interface that is provided would be things like you can check a book in, you can check a book out, you can reserve books, you can pay fines, etc. Those would be the operations that the ADT specifies. The data structure, which is really internally how these elements are being stored and manipulated, the books could be stored randomly. They could be just tossed in a big bin, and then they would have to look through all of them to find anything. Probably not very efficient, but or they could be sorted alphabetically by title or by author, or you could use the Dewey Decimal System or some other sorting scheme. But the whole point here is that the users of the library don't need to know anything about how it actually does it. They simply know the operations and the interface that's being provided, and that's how they deal with the books in the library. So you can look at this as having multiple levels. There's that level, the outside level. There is the logical level. This is the abstraction that an ADT provides, and then that answers, for example, a bunch of what questions, like what do we do to the data? Those are the definitions that an ADT would model. Then we've got the implementation or the coding level. That's the sort of lowest level, most specific, and that answers more the how questions: is how was this how is the collection and the operations on the collection, how are they actually implemented? Those are what are the concrete data structures. So here's our library from the user's perspective, which is the application level. All they know is they want to check out a book, they need to pay a fine, etc. But the data abstraction level, here's the lady, is shielding him from that. He doesn't need to know any of that, but she says, I can do this for you, I can do that for you, etc. And then the implementation would actually be the the organization. Where is the reserved? Where are the reserve books kept? How do I find something? That isn't on that shelf. That is the actual analogy to the implementation. So the data levels of a library here we've got from the application level, that would be the Library of Congress, the New York Public Library, like the picture here of that's actually one of the two library lions, Patience or Fortitude, as they're known. The logical level would be the collection of books that is housed there. The operations, again, as we just saw, the standard library operations. And then the implementation level would be actually, how is a book stored? How is it referenced? How is it found? How is it physically retrieved? Etc. Okay, so there's our analogy of a library, hopefully making this somewhat clear. So from a programmer's perspective, back to our view of the world here, the application programmer has access to the class, which defines what kind of data it's talking about, what it contains, and then those operations that can be done with it. And the application programmer doesn't need to know anything at that point about how the implementer has actually implemented it. Okay, and the beauty of this, to cut to the chase here, is that the ADT implementer, if they come up with a better mechanism or better scheme for storing or manipulating the data underneath, as long as they don't change the interface that the application programmer is using, then they can actually improve or extend the capabilities of the class without the application programmer or their code having to change. That's a very powerful concept in system design.